Stars appear in different colors due to their temperatures. Blue stars are the hottest, reaching up to 30,000 degrees Celsius or more, while red stars are the coolest, with temperatures as low as 3,000 degrees Celsius. Yellow stars, like our Sun, have temperatures around 6,000 degrees Celsius. Each star emits a spectrum of colors, but the color we see is the brightest one in that spectrum, which directly depends on the star's temperature. Imagine a piece of iron being heated. It first turns red, then orange, then yellow, and finally blue if it reaches a very high temperature. The same applies to stars. Imagine that the universe is not something inside a box, but rather the box itself. The expansion of the universe is not an expansion into a pre-existing vacuum, but rather an expansion of space and time themselves. There is no outside to expand into. Rather, expansion is an inherent property of the universe. In other words, the distances between galaxies are constantly increasing, and this is not because galaxies are moving through space, but because space itself is expanding between them. This expansion began after the Big Bang, approximately 13.8 billion years ago, and continues to this day, accelerating due to dark energy. The Big Bang was not an explosion in the usual sense, but rather a very rapid expansion of the universe from an extremely dense and hot state. The sound we refer to here is a theoretical representation of changes in the density of the early universe in the form of sound waves. These sound waves, which propagated through the cosmic plasma in the first approximately 380,000 years after the Big Bang, left their mark on the distribution of matter in the universe, which we see today in the form of galaxy clusters. We cannot hear this sound directly, as it is not sound in the physical sense that we perceive with our hearing. Rather, it is a mathematical model that helps us understand how the early universe evolved. Scientists have converted this data into an audible scale for representation, but this is merely a representation and not the actual sound of the Big Bang. Imagine approaching a black hole. The enormous force of gravity begins to affect you. However, the gravitational force is not equal on every part of your body. The part closest to the black hole experiences a much stronger gravitational pull than the part farther away. This vast difference in gravitational force creates what resembles a terrible stretching or elongation process. Your head, for example, is pulled more forcefully than your feet, causing your body to stretch vertically. As you get closer, this stretching increases wildly. Eventually, the force of gravity overcomes any force holding your body's atoms together. Simply put, your body is torn apart into small pieces, then into molecules, and finally into individual atoms. This terrifying process is called spaghettification. Yes, there is what is known as the dark side of the moon, but calling it dark is somewhat misleading. It is actually the far side, because it never faces Earth due to a phenomenon known as orbital synchronization. This far side is not completely dark. It is exposed to sunlight just like the near side, but it is less visible to us from Earth. What is there? Completely different terrain. Many more impact craters and fewer dark lunar plains compared to the near side. Additionally, there is the South Pole Aitken Basin, the largest known impact crater in the solar system, and scientists believe it may contain valuable information about the moon's formation. Finally, because it is shielded from radio interference from Earth, the far side is an ideal place to deploy giant radio telescopes to study the early universe. In 2019, China's Chang'e 4 spacecraft landed on the far side, marking the first soft landing on this side of the moon. If you traveled at the speed of light, theoretically, time would stop passing for you compared to a stationary observer. This is due to the effects of Einstein's theory of special relativity. As your speed approaches the speed of light, time slows down for you, and if you reach the speed of light, it would theoretically stop completely. However, in practice, this is impossible for objects with mass. Accelerating an object with mass to the speed of light requires an infinite amount of energy. Moreover, even if it could be achieved, the effects would be extremely complex, and stopped biological aging may not be the only or most accurate outcome to describe what would happen. We do not know for certain where the edge of the universe is, or even if it exists at all. The observable universe, the part we can see from Earth, extends about 53 billion light-years in all directions. This means that light from the most distant objects we can see would have taken 53 billion years to reach us. What lies beyond the observable universe is pure conjecture. The universe may continue to expand indefinitely, or it may have a definite end, but we currently have no way of knowing. There are various theories, such as the idea of the multiverse, which suggests the existence of other universes beyond our own, but these remain speculative. Simply put, the limits of our current understanding stop at the boundaries of the observable universe. Yes, the multiverse theory is a controversial scientific hypothesis that proposes the existence of an infinite or very large number of other universes alongside our own. These universes may be completely different from ours, with different physical laws, or exact copies with slight variations. Several theories support this idea, such as the theory of eternal inflation, which indicates that the universe is constantly expanding and parts of it stop expanding to form new universes. Additionally, quantum mechanics allows for the possibility of multiple states of particles, with each state existing in a different universe. Of course, there is no definitive proof of the existence of the multiverse yet, but scientists continue to research and explore this idea, which could radically change our understanding of the universe. This idea dates back more than 53 years and is still under study. Dark matter is an invisible substance that does not interact with light or any electromagnetic radiation we know of. We know of its existence through the effect of its gravity on galaxies and stars. Dark matter makes up about 85% of the total mass of the universe. We do not know exactly what dark matter is, but there are many theories, including that it consists of new elementary particles we have not yet discovered, such as axions or weakly interacting massive particles, WIMPs. Understanding dark matter is one of the greatest challenges in modern cosmology.